I'm continuing off part 1. So in the last video I found the error line and I drew my error bars. So in this video I'll be helping you carry on from that. So the next thing we need to do is find our mathematical equation, which if I go back to the document, it is this thing right here, okay? And I'll show you what each thing is. So remember, the y is the dependent variable, which is t. The m, this is the mass transformed, right? This is not the mass, this is the gradient, okay? So don't get those two things confused. This is the gradient. It should be a lowercase m, but just ignore that. This is the uncertainty symbol, it's delta, so I'm just gonna do this. Equals gradient uncertainty, right? And then the square root of mass is obviously the independent variable transformed, right? Formed. And then C is the y-intercept, which is given to you on the software. And obviously this is the uncertainty of the y-intercepts. Right, so we need to find, we are given this, okay? We're given that, and we're also given this. These two just remain as variables. You're just going to change this y to a t, so it becomes like this. You're not plugging in numbers here. These stay the way they are. You're only going to be plugging in numbers for m, this m here, c, and this c here, right? So we need to find the uncertainties of the gradient and the intercepts. That's what we need to do now. So this is for a different graph because I did another one the other day, so it's not going to be the same, but I'll tell you how you can do it, but I'm not actually going to carry out the calculation here because this Word doc's really annoying. So you just need to pick 2 points that are quite easy to sort of read from. So maybe if I go from this point here all the way down. Actually, let's do this coordinate here first. So that's around 0.055 and 0. And then up here it would be roughly, I would say, 0.255 and 0.3. So those are my coordinates. This is my x1, y1, x1, x2, y2. The gradient equation for the error line is this here. Pretty much just rise over run, x2 minus x1. So you would do that, and that would give you your, you call this m dash so you don't get confused with this gradient, because remember this is the gradient of your best fit line, so the red line which the software generates for you, so you don't need to find that gradient. So once you've found this error line gradient, you would plug it in. So to get the uncertainty of the gradients, it's literally just your best fit gradient, which the software gives you, minus the gradient, which I just told you how to calculate. That would give you your uncertainty. And then you would put it in place of this sign here. So that was from another example. That's a different graph, remember, so the numbers won't be the same. So now we just need to find the C, the y-intercepts. So you're given one of the y-intercepts already. So this was the y-intercept of the best fit line. So to find the intercept of the error line, you just read it off the graph. So for this one here, it would be, this is your C dash here. That's around 0.055, right? Negative because it's going through the x-axis, so it's not a positive anymore. So you would take that, so you'll change your y-intercept uncertainties would equal your intercept of your best fit line, which they gave you here, minus this value here, your C dash, and that will give you your y-intercept uncertainty. So if we go back to the document, I've done this, different numbers for another graph. And then remember, you need to round all your uncertainties to one significant figure. So this becomes 0.6, and this becomes 0.2. And notice how the other variables also match the same dp. So you can't have something that looks like this, for example, for the gradient, right? That would be wrong because these dp's don't match. Same goes for the intercept. So you've got to make sure it's one significant figure for the uncertainties. And other variables match decimal points. Okay, that's your final mathematical equation for the practical. And so once you've found your final mathematical equation, you need to find the theoretical gradient so you can compare your gradients. So this is the gradient, right, of your practical experiment. So now we need to find the gradient of the theoretical equation so we can compare the two and see how accurate our experiment was. So this is the theoretical equation here, right? You can see our independent variable in there and our dependent variable here. So the first thing, and I've also provided us with what EI is. Remember the length, you decided what the length was. Remember, it's the distance that extends outwards from the table, so past the clamp. My group, it was 0.8 meters. So this part here, I've just taken out the m because that's not necessary, so you can write it as like this, right? I've taken out my independent variable, and I also ignore the t. So ignore that and ignore the mass, so you're left with this. This is your theoretical gradient here. So all you need to do is plug in a value for L and plug in a value for EI, which they give you what EI is here. That's on the assessment instructions, so you do need to read that document as well when you're doing the assessment. So once you plug all that into your calculator, you should get an answer of 1.676 ... because it goes on for ages. So now we have to find the uncertainties of our controlled variables that goes with the gradient. Okay, so our two controlled variables is L and EI, obviously. So the first thing, I'm going to calculate the uncertainty of the flexibility, so EI first. So we're going to find the fractional uncertainty first. Now before we do anything, right, we need to know what the power factor is. So if we go back to our equation here, if we just focus on EI, we can see that it's got a square root over it, right? And also I just put 1 here because can't have nothing. So if we want to convert that to a power form, it will become this, to the power of -1/2, right? It's a negative because it's on the bottom row. If it was just like this, that would become a positive. But it doesn't matter if you have negatives, you treat them exactly the way as positives. So the negative doesn't really matter, just sort of pretend it doesn't exist. So that's your power factor there, okay? So you would take your standard uncertainty that they gave you. So for the equation here, you got your standard uncertainty, which they gave you. See here, 0.9. So I would plug in 0.9, and it's over the actual value of the controlled variable, EI. So in that case, it was 2.4, right? Because here it is, 2.4. And then you would multiply this by the power factor, which we found was 1/2. Just ignore the negative, like I said. That will give you a fractional uncertainty of 0.1875. This is not a percentage uncertainty, so what we're going to do now is multiply this by 100, and that will convert it to a percentage uncertainty, which I found here. And you would repeat this for the uncertainty of L, but remember, L has got a different power factor and different standard uncertainty. So remember, they haven't given you a standard uncertainty of L, so you just have to assume it's the lowest scale division, which is 1 millimeter, or if we convert that to meters, it's 0.001 m, which is what I've got here. And the 0.8, remember, is the length that you picked, right? So this is your form with its standard uncertainty. So we go back, finding the power factor now. You can see that it's L cubed inside a square root. Now remember, we raised the square root to a power of a half. Now that looks kind of funny, right? So that becomes this. You just divide the 3 power by 2. So your power factor would become 1.5. Because 3 divided by 2 is 1.5, right? So that's your power factor. Okay? So same steps as up here. Your standard uncertainty, which in this case is 0.001, divided by your actual value, 0.8, multiplied by your power factor, 1.5, and that will give you this, your fractional uncertainty. And again, to convert it to a percentage, multiply it by 100, and you'll get your percentage uncertainty. So, to find the absolute uncertainty of the theoretical gradient, which is the last step we need to do before we can compare the two gradients, there's 2 ways you can do this. You can add the total fractional uncertainties and then just multiply it by the theoretical gradient. So your 2 values here, 1 and then 2, you add them together, put a bracket around it, or else if you put in your calculator this, and you multiply that by the 1.67, it's going to multiply it onto this, and then you might get a different answer. So you need the brackets because these 2 are being added together. That will give you plus or minus 0.3, and then remember we round it to one significant figure. Or you could add the percentages, but then to convert it back into a number, we want to divide by 100. This method is kind of meaningless because you need to convert it back into a normal number anyway, so I don't understand. You should just do this, but hey, the teacher sort of liked this method. He highlighted it blue, so maybe you can do this. Just add the percentages and then divide it by 100 to convert it back to a normal number, and then multiply it by the theoretical gradient, and you'll get the exact same answer. So that is the theoretical gradient with the uncertainty. Now remember, this was the 1.676, but you have to round it to the same dp to match, right, the uncertainty. That was our practical gradient uncertainty. So as you can see, comparing the ranges, and you just need 2 sentences saying it either completely agrees, partially agrees, or completely disagrees. You just need to talk about that, and that will wrap up your final merit mark. Cool, that's part 2 done, and that's probably it.